Right, let's look at factorising over complex numbers. We'll start with the Fundamental Theorem of Algebra, where it says that, and this theorem says that every expression p is a function of z equal to an z to the n plus an minus 1 z to the n minus 1 plus all the way down to a1 times z plus a0, where the an are not equal to 0 and where n is a natural number and the coefficients are complex numbers. So we're saying the coefficients of the z here are complex numbers, but let me just remind you that the real numbers are a subset of the complex numbers. So these an can be real as well. Okay, now, what's that theorem saying? Well, it's saying given all that, n is a natural number and the coefficients are complex numbers, then it has at least one linear factor in the complex number system. So this polynomial here will have at least one linear factor in the complex number system. Okay, and by applying this theorem repeatedly, it can be shown that a polynomial of degree n can be factorized into n linear factors in the complex numbers system, so that p of z can be written an times z minus alpha 1 times z minus alpha 2 times z minus alpha 3 all the way to z minus alpha n, where alpha 1, alpha 2, alpha 3 all the way up to alpha n belong to the complex numbers. Okay, and one other thing just before we begin and put some applications here is the conjugate factor theorem. Now, if the coefficients of p of z are real numbers, so if the coefficients of p of z are real numbers, that's these an here, then the complex roots occur in conjugate pairs, such that if z minus alpha 1 is a factor, then so is z minus alpha 1 conjugate. Notice the bar above, the conjugate, the bar indicating the conjugate. So if z minus alpha 1 is a factor, then so is z minus alpha 1 conjugate a factor, okay? That's where the coefficients of p of z are real numbers and the complex roots occur in conjugate pairs. All right, let's first use of this, first example. Let's say p of z is 4 times z squared plus 16. Okay, let's factor out the 4, so we have 4 outside of z squared plus 4, 4 outside of z squared plus 2 squared. Okay, now clearly the coefficients here are real numbers. Okay, well then what that means is when we come down to this line here, the fourth line, 4 times z squared, what we can do is a slight trick. We can put I squared in here. Remember, I squared is equal to minus 1, but then we also need to turn this plus here into a minus. Okay, so I squared is minus 1, but then we put a minus here, so that cancels out, and we're left with just the 2 squared we had above. Okay, leaving that in there gives us this flexibility because we can now write this as 4 times, in brackets, z squared minus 2i all squared. All right, okay, and then difference of perfect squares, a squared minus b squared has this format over here. So that means we can use a difference of perfect squares to write 4 times in the brackets, and then in the first set of parentheses, z minus 2i, times in the second set of parentheses, z plus 2i, okay, difference of perfect squares. Okay, and I can lose the square brackets there and just simplify it down to 4 outside of z minus 2i times z plus 2i. And we're able to do that because we now see the z squared here, we had a real coefficient here. Okay, so the coefficients are real in this case. So we end up with a repeated linear factor. They have to be 2 factors because this is a square quadratic, so they had to be 2 factors. Okay, and what we got is 2 complex factors. Okay, let's have another look one. Here's another quadratic. Okay, I'll just scroll down a bit. Let's get that fully into view. Okay, here we go. 3z squared plus 3z plus 1. Let's factor out the 3 here. Okay, now we can sort this out by completing the square. So we've got z squared plus z. And then we're just going to add on, when I say b on 2, where on earth did the b come from? That's just my notion of saying, here is the b part here. Okay, here is the b there. Okay, I'd call that b and I'd call that a c. Okay, so I'm going to add on this b on 2. Okay, which now b in this case is the coefficient of z here inside the parentheses, which is a 1. So we're going to have next one down 1 over 2. Okay, what I add I need to take away as well in order to keep this expression the same, otherwise I'd be wrong. So what I've got, next line down is 3 outside the brackets, z squared plus z plus that 1 from here, the 1 over 2 all squared, plus the third we originally had, and then I'll take away what I've added, so minus 1 over 2 all squared, just standard technique for completing the square. All right. What we have now, next line down, is 3 outside of z plus a half all squared. If I expand out z plus a half, what I'll end up with is z squared plus z plus a half squared. Okay, then I've got plus a third minus a quarter here. Okay, when I combine that, 1/3 minus a quarter, I'll get 1/12. All right, z plus a half squared plus 1/12. And again, same thing here. That plus positive here, I can put a minus in, as long as I put where the 1 is, I put I squared, because I squared is minus 1. Minus and minus gives it, keeps it positive. Okay, and again, same thing here, difference of perfect squares I did in the previous example. So let me just scroll down to the next bit. Here we are. I'll keep the top of the page there. So here I've got, I can write that as difference of perfect squares, z plus a half all squared, minus I on the square root of 12 all squared. Okay, and then that gives me, writing that out as factors, as z plus a half minus I on square root 12 times z plus a half plus I on square root 12. And I've got two complex factors. Okay, let's just take this a little bit further. Another example now. Let's look at z to the power of 4 minus 9. Okay, well, I could write that as z squared minus 3, difference of perfect squares if you like, times z squared plus 3. Okay, because if I expand that out, I'll have z to the power of 4 minus 9. And what can I do there? Well, I could write, see that minus 3, I could write that as minus square root of 3, all squared, all right, times z squared plus 3. Okay, what else could I do with that? I know there's got to be 4 factors. How am I going to get 4 factors? Well, with this difference of perfect squares here, I can get 2. That's these ones here. Z minus square root of 3, z plus square root of 3. Okay, that's fair enough. That's got 2, and I've still got 1 more here, but I really need 4, don't I? And this is where, again, see, I've got z squared plus 3. What I can do, oh, notice here the factors of here, the coefficients of this polynomial are positive. They're all real numbers, sorry, real numbers. My apologies, real numbers. Okay, so what we've got down here now, let's come down this line, z minus square root of 3, z plus square root of 3, and I'm going to put this I squared term in again, okay? Because I squared, good old I squared is minus 1. So if I put I squared in here, that's equal to minus 1 times negative 3 will give me plus 3. Okay, now that's opened up opportunities for me here. And what I've got now is z, next line down, z minus root 3 in parentheses times z plus root 3 in parentheses times difference of perfect squares, z minus square root of 3 times I in parentheses times z plus square root of 3 times I in parentheses again. So now I've got my 4 factors, 2 of them real and 2 of them complex. Okay, another example. Okay, now let's have a look at another question. If z equals 2 minus square root 3 of I is a solution to z squared minus 4z plus 7 is 0, what is the other? Well, why did I ask that? Well, if you have a look here, the coefficients of this polynomial, real and real. All right, and the end term is real too. So real, real, okay, and that tells us by the conjugate factor theorem, the other solution must be given by the conjugate of the first solution. So z conjugate is a conjugate of 2 minus root 3i, which is 2 plus square root 3i. Because remember, the conjugation operation only changes the sign of the imaginary part. And p of z, of course, has real coefficients. So the two solutions for this quadratic here are 2 minus square root 3i, 2 plus square root 3i. All right, next one down. Where are we going to? If z1, here we go. I'll just scroll it down a bit. All right, if z1 is 2 plus square root 3i, is a solution to the polynomial p1 is z cubed minus 5z squared plus 11z minus 7 is 0. What are the others? Okay, we've got 1. Now, since the coefficients of p of z are real, that's real, that's real, that's real, they're all real, are real, all of them, Then by the conjugate factor theorem, the next factor, there must be another factor, which is the conjugate of the first. So the conjugate of 2 plus square root 3i is 2 minus square root 3i. Okay, we've got two solutions. Now, if we multiply these two solutions, if they're combined, so we multiply them together, expand them out, collect like terms, sort it all out, tidy out, we get the second polynomial. Here's another polynomial, quadratic, in power is z squared minus 4z plus 7. Okay, so we've got two solutions already. We've got z1, z2, and we just need one more solution to our cubic here. Okay, so what we can do is polynomial division. Okay, so we can divide P2, our new polynomial, z squared minus 4z plus 7, into our original P1, okay, the cubic here. Okay, dividing lead terms in, z cubed divided by z squared is z. Okay, then we multiply z by this object here, so we get z times z squared is z cubed, z times minus 4z is minus 4z squared, and z times 7 is 7z, and we're going to subtract that from the original up here, so z cubed minus z cubed is 0, minus 5z squared minus 4z squared, well, that just gives us minus z squared, 11z minus 7z will give us 4z, minus 7 minus 0, okay, will just give us minus 7, so we've got minus 7 here. Now let's divide again. All right, z squared into minus z squared is minus 1. Minus 1 times z squared is minus z squared. Minus 1 times minus 4z is plus 4z. Minus 1 times plus 7 is minus 7. And then when we subtract these two, we just get 0. So 0 remainder. There's no remainder here, so it divides evenly in. And so what we've got then is this cubic here, P1, right, is equal to our new factor we discovered here, z minus 1 from the polynomial division, times this other polynomial we generated through the conjugate factor theorem, z squared minus 4z plus 7. So there's our three factors, right? Z minus 1, 2 minus root 3i, 2 plus root 3i. Okay, let's keep going a little bit further. And that's that one done for now.